So if you look on the left-hand side of this inequality we have to prove, you can see that there's two terms for each of those brackets. So, and you can see that the last one has a 2k. So if I halve that, you can see there must be k terms, right? So if I, for example, I looked at this and I went to the 6, half of that is 3 terms. So there are 3 terms there. So I'm halving that 2k, and I know there are k terms, so something worth noting. All right, we could write them a different way. So if I look at that left-hand side and make a common denominator, I would be doing 1 times 2, and you can see you'd get 2 minus 1, which is 1. If I did the same thing here, 3 times 4, I'd get 4 minus 3, which is 1. So you can see each time we are going to get a 1 in the numerator. And so that would give me right up to 2k minus 1 times my 2k, and I'm going to get a 1 there. Alright, now you can also see that that is going, it's an inequality, so we're not looking for equals, we're looking for the top there to be greater than something. So I'm going to put something under the bottom, under the denominator, that's even bigger than this one. So we're getting bigger and bigger and bigger until this last bit here. So if I put something bigger under it, in the denominator, then the whole fraction will be smaller. Yep, so what I'll do is each and every one, I'm going to put the next one, which is the next one after this would be 2k plus 1, 2k plus 2, there we go, 2k plus 2, and I'm going to keep putting them in for each one, yeah, because you see that's my denominator on this side, so I know that's what I want. And right up to the last one, I'm replacing it with this denominator that's bigger. So since this denominator is bigger, the whole fraction is smaller. So this whole part on this top line is going to be larger than this whole part on this side. And we know there are k terms, so I'm going to get k lots of, I've done that exact same one, so k lots of these fractions is what we're going to get. So then we do get that inequality there. Okay, so remember we're going to use that because it says hence and we're proving. So just remember we're going to use that. Pop it in as soon as you see you can. Alright, so this is for n is greater or equal to 2. So when I let p of n be the proposition, my base case is going to be 2. So let's have a check out of our p of 2. So my left hand side here will be, it's a little different from a. It's going to be 2, and if I put a 2 in there, I get a 4 minus 1 is a 3. So I know I've got the first term and the second term. 1 plus 1 on 3. Okay, so that's 8 on 3. Or let's say 2 and 2/3. Whatever's easy to compare. My right hand side then is going to be 2 plus 1 in the first bracket. And again, if I put a 2 in there, I get a 4. So I know I've got those first 2 terms. So I've got a half and a quarter. Which is 3/4, and we're timesing by 3, so we've got 9/4. So that's 2 1/4. Alright, so clearly the left hand side is greater than the right hand side, so we're all good there for p of 2 for the base case. So the assumption is our p of k for some integer k, and that would mean that k outside of 1 plus all those, and that'll be 2k minus 1 is greater than k plus 1, and then we've got a half plus a quarter all the way to 1 on 2k. So that's our assumption we're going to use. What have we got to prove? We're required to prove p of k plus 1, which would be k plus 1, lots of 1, again, all the way to that 1 on 2k minus 1, but also we're going to add in a 1 on 2k plus 1. And that we want to show is greater than, so that's going to be a k plus 2, that's going to be half, so all the even denominators now, up to the 2k and including a 2k plus 2. Okay, so that's what we're required to prove. So let's have a look at our left hand side, and you can see that if we break up this bracket here, so we've got k times 1 plus, and let's just go to 2k minus 1. Okay, so we've left this one out. So we've still got k lots of that one as well. Just note. Alright, I should write that down, shouldn't I? So I've still got, actually let me do this first, and then, so it's k, I've used the k up for these ones. Now I'm going to use the 1 up, so I've also got 1 lots of everything in that bracket. But then I need my k plus 1 lots of this last one here. So I've got k plus 1 lots of this last one here, which is a denominator of 2k plus 1. So that's just breaking up the brackets a little bit so that I can use my p of k. So you can see now I can use my p of k for this bit here. So I can say, okay, that top line is now going to be greater than k plus 1 lots of a half, a quarter, all the way up to 1 on 2k. But I've still got all of this stuff left. And if you have a look, I don't want this one's got the odds. I don't want the odds because look at what my k plus 1 is. It's just the one with the evens. That's a bit of a hint. So why don't we take this one, and so we've got all those odds, but remember we want to use part A. So if I just add in a minus a half, so I know the third's there. So if you can, I didn't write it out very well, but the third's in the odds, but let's add in minus a quarter, etc. all the way up to, so we've got the 1 on 2k minus 1. Let's add in the minus 1 on 2k. Oops, there we go. So what have I done? I've subtracted a half, so to balance that I've got to add a half. I've subtracted a quarter, so I've got to add a quarter. All the way up to I've subtracted a 1 on 2k, so I've got to add that back in. And then don't forget I've still got this term, which is my k plus 1 on 2k plus 1. So I've manipulated that middle bracket there so I can use part A there. So again, I can say, well, this top line, I'm about to sub in something that's smaller. So that top line is greater than k plus 1. I've got the evens, so that's all good. I want the evens denominators. And then this part here, I'm subbing in k on 2k plus 1, 2k plus 2, and then I've got, you can see I've got another one of these even brackets. So actually if I put it together with that one, I've got k plus 1 of those plus 1 of those. So let's change that to a k plus 2 of those. Then I don't need to write it out again. Okay, so that's that one. But I still have this last term, so plus k plus 1 on 2k plus 1. Alright, so you can see that's looking good because I've got the k plus 2 that I want, and I've got the bracket but up to there. So let's have a look at what we kind of end up with our last fractions. So if I put them together, so what am I putting together? I'm putting these two together. I'll just have a look. The common denominator would be 2k plus 1, 2k plus 2. So above, I'm going to get that k, but I need a 2k plus 2 lots of the k plus 1s. Now that gives me, on that top, it's a 2k squared, it's a 5k, and it's a 2. Yeah, that's right. So that's just the numerator is equal to that. And I can factorize that. And I know, if you think about it, I need to get rid of that 2k plus 1. So I know one of the terms is going to be 2k plus 1, hopefully. And then I can, work out the other one. It's not 2k, it's going to be k plus 2. Right? That would give us the right answer. So we get 4k plus 1k is 5k, and 1 times 2 is 2. So if I do that, so I've changed, what I've done is I've changed this top, I've expanded it and factorized it, refactorized here. So I did it again, that should be a k plus 2. So now that cancels, which is what I wanted, and so this whole thing here is equal to a k plus 2 and a 2k plus 2. So I can factorize those two terms now because of this k plus 2 and this k plus 2. So it's equal to, if I factorise by that k plus 2, I've now got the half all the way to the 1 on 2k, but I've also got this on the denominator, so I've also got the 1 on 2k plus 2, which is what we wanted. So now we've got that one. So it does work, just remember you're using part A as well as using your P of k to do it. And you've got all the other little steps that the P of k implies P of k plus 1, etc.